In this lesson, we will study one-sided limits, they are limits as x approaches some number, let's call it c, from the left-hand side or the right-hand side. Consider the following function. F of x is equal to x divided by the absolute value of x. Now, if x is positive, then this is just x over x, which is equal to 1. If x is negative, then these two values are opposites. So then the quotient is equal to -1, right? Here's the graph. Notice that the function is undefined at x equal to 0, of course, because we cannot divide by 0. So this is the graph. Now, what I would like us to consider is the limit of this function as x approaches, let's say, 0. Now, what's interesting is as x approaches 0 from the right, your function values are approaching 1, while as x approaches 0 from the left, the function values are approaching something different, -1. Because these two limits are different, we're going to say that the limit of f of x as x approaches 0 does not exist. That is to say, the only way a limit exists is if it's the same number, right? The limit is the same number from both sides of, well, in this case, it's 0, right? As we were considering as x gets closer to 0. As x gets closer to 0 from the right, your function values are approaching 1, but as x approaches 0 from the left, your function values are approaching -1 because those two values are not the same. Because those two limits are not the same, we're going to say the limit of f of x as x approaches 0. Basically, when we write it like this, as x approaches 0, we mean from both sides of 0. It does not exist. All right, so this is sometimes called a two-sided limit, right? As x approaches 0 from both sides of 0. So although the two-sided limit does not exist for this function, what does exist is a one-sided limit. That is to say, the limit, like we said a couple times now, as x approaches 0 from the right, your function values are approaching 1. That's a one-sided limit, or a right-hand limit. Okay, this is as x approaches 0 from the right, so then this is a right-hand limit, or a limit from the right. The limit as x approaches 0 from the left, this is a left-hand limit, or a limit from the left, and it is -1. This is how we write it. This says the limit of our function as x approaches 0, watch this, from the right, that's what this notation means, from the right, is equal to 1. So this is what we would call a right-hand limit, or a limit from the right. Now, let's consider the limit as x approaches 0 from the left. This is our notation, the limit of our function as x approaches 0 from the left. This is how we write that, is -1. This is a left-hand limit, or a limit from the left. So again, I would like to reiterate that this limit here, before this lesson, we've been studying two-sided limits. We never really called them two-sided limits, but now we can see they have been two-sided limits. The only way a two-sided limit exists is if the one-sided limits are the same, if they are equal. And again, these one-sided limits are not equal, therefore the two-sided limit does not exist. This summarizes our findings, I think, pretty well. Suppose that a function f is defined on an open interval containing c, except perhaps at c itself. Remember, in order for the limit to exist, we do not need the function to be defined at c, right? Then f of x has a limit as x approaches c, if and only if it has a left-hand and right-hand limits there, at c, and these one-sided limits are equal. So the limit of f of x is equal to L as x approaches c. This is a two-sided limit. Right here, when we say as x approaches c, we mean as x approaches c from both sides of c. As x approaches c from the left and from the right. If and only if, this is the symbol for if and only if, these one-sided limits are equal. They're both L, okay? Now, if and only if means that this statement works in both directions, right? So, let's see. The limits, if you can show that the limit, this one-sided limit is L and this one-sided limit is L, that must mean that the two-sided limit is L. And that works the other way around. If you can show that the two-sided limit is L, that must mean that this one-sided limit is L and this one-sided limit is L. So this statement works in both directions, if you will. Okay, let's consider this function. F of x is equal to the square root of 4 minus x squared. Let's see if we can get the graph of this function. Remember that f of x is function notation for y. So I'm going to replace f of x with y. And then what I'm going to do is I'm going to square both sides. So y squared is equal to 4 minus x squared. And then I'm going to get x squared and y squared, my variables, on the same side of the equation. So an equivalent equation is x squared plus y squared is equal to 4. Now, you and I know what this is, right? If we graph, this is a circle centered at the origin whose radius is 2. So then the graph here, I mean, don't judge my circle too harshly, okay, folks? But this is a circle, supposed to be a circle, centered at the origin of our plane with radius 2. However, let's go back to the original function of how it's written, or even here, y is equal to the positive square root of 4 minus x squared. Sometimes we use the word principal square root. So y is not equal to plus or minus. It's just equal to the positive square root. So y is equal to, or your function values are equal to positive, the positive square root of 4 minus x squared. In other words, this function here only defines the upper half of the circle because that's where it's positive. That's where your function values are positive. So we actually have to omit or scratch off or disregard this bottom half. So here, I've updated our picture. So it's only a semicircle, right? The upper half of that circle, centered at the origin here with radius 2. All right, so this is technically, this is what the graph looks like. All right, very good. Now what I would like for us to consider is the one-sided limit as x approaches, let's say -2 from the right, and the limit of this function as x approaches 2, positive 2, from the left. Let's consider those two limits. All right, so I have here the limit, this is a one-sided limit, the limit of our function as x approaches -2 from the right. Let me just show you that really quickly. As x values approach -2 from the right, your function values, be careful, your function values are not approaching -2, right? -2 is the x value. We're talking function values. Your function values are approaching 0. So then this limit here, this one-sided limit is equal to 0. Now, as x values approach +2 from the left, let me see if I can show that. As x values approach +2 from the left, right, your function values are approaching 0. And so this limit here is equal to 0. Now, what's really important is that you and I understand that this function does not have a left-hand limit at -2. The reason is because the function is not defined to the left of -2. It does not have a right-hand limit at x equal to +2 because the function is not defined to the right of x equal to 2. The function does not have a two-sided limit at either -2 or at +2 because f is not defined. on both sides of these points. F is not defined to the left of -2. F is not defined to the right of +2. So all we can say is that the function does have a one-sided limit as x approaches -2 from the right, and that the limit, or the function, excuse me, has a one-sided limit as x approaches 2 from the left. Okay? I hope that's clear. Let's move on. Now, I must be clear about something. I'm going to scroll back up to our previous definition. Here it is. This definition here, we said that this is a two-sided limit here. And this two-sided limit exists, and it is L, if we can show that the one-sided limits, as x approaches c from the left and as x approaches c from the right, are both L. Now, this applies to interior points, okay? Interior points of a function's domain. For example, for this function here, the domain of our function, let me see if I can be clear here. I'll just put capital D for domain. The domain of our function is -2 to +2, okay? Now, this function has a two-sided limit for every value, or at each point inside the open interval -2 to 2. Oops, sorry. Let me see if I can rewrite that. -2 to 2. This is an open interval, all right? And that's why up here, I'm sorry to be going back and forth here, we're saying suppose that a function f is defined on an open interval. So for this function here that we have, on this open interval here, this function does have a two-sided limit. It does, at every single point inside this open interval. All right, so, but what you and I were looking at right now are these boundary points. -2 and +2 are not interior points. They're not interior points. They are boundary points, okay? And what is true is that at a boundary point of its domain, a function does have a limit when it has an appropriate one-sided limit. Let's write that down. So I'm sorry, I miswrote this. So sorry about that. At a boundary point. At a boundary point of its domain, a function has a limit when it has an appropriate one-sided limit. So for example, -2 is a boundary point. And because at -2 there is a one-sided limit, we found that, right? We have a right-hand limit at -2. Then we can say the following. The limit of our function as x approaches -2 is equal to 0. The limit exists. Likewise, 2 is a boundary point. It's not an interior point. It is a boundary point. And because this boundary point does have a one-sided limit, it has a left-hand limit, right? We can say that the limit of our function as x approaches 2 exists. The limit of our function as x approaches 2 exists, and it is equal to 0. So when talking about boundary points, all you really need to show is you need to show that there is a one-sided limit. If you can show that there's a one-sided limit at the boundary points like you and I have, then we say the limit exists at that point. To make this point more clear, let's look at this function that I've graphed for us, okay? Let's call it f of x. First of all, notice that your endpoints or your boundary points is 0 to 4. So this function is defined from 0 to 4. That's the domain of this function. So 0 is a boundary point, 4 is a boundary point. All right, what I would like us to do is consider the limit, a lot of limits actually. Let's consider the limits as x approaches 0, x approaches 1, 2, 3, and 4. Let's start. Okay, first, the limit of our function as x approaches 0 from the left. Now, as x approaches 0 from the left, wait, hold on. The function is not even defined to the left of 0. 0 is a boundary point. The function is not defined to the left of 0. Therefore, the limit of our function as x approaches 0 from the left does not exist. Okay? The limit of our function as x approaches 0 from the right. Now, we can talk about that. As x values approach 0 from the right, your function values are approaching 1. So this is equal to 1. Now, because 0 is a boundary point, we will say that the limit exists at x equal to 0, right? Or as x approaches 0. The limit exists because we have a one-sided limit, right? X equal to 0 is a boundary point. So as long as there's a one-sided limit that exists here, we will say the limit of our function as x approaches 0, it does exist, and it's equal to 1. Let me say is equal to 1. All right? Now let's look at x equal to 1. Now, 1 is not a boundary point. 1 is an interior point. Okay, now the limit as x values approach 1 from the left. As x values approach 1 from the left, your function values are approaching 0. All right. As x values approach 1 from the right, your function values are approaching 1. Now, the only way this two-sided limit exists for this is an interior point, the only way the two-sided limit exists as x approaches 1 from both sides is if these two one-sided limits agree, or that they are the same, and they are not the same. Therefore, we're going to say the limit of our function as x approaches 1 does not exist. All right, very good. Now let's go to another interior point, namely 2. All right, let's consider now the limit of our function as x approaches 2 from the left. All right, here we go. X values are approaching 2 from the left, and your function values are approaching 1. All right, very good. The limit of our function as x approaches 2 from the right, okay? As x values approach 2 from the right, your function values are approaching 1. Alrighty. This is a two-sided limit, all right? The limit of our function as x approaches 2 from both sides is equal to 1. So notice that this two-sided limit is automatically 1. I didn't even have to look at the picture or the graph because these one-sided limits agree. So once these two one-sided limits agree at 1, right? I know automatically then the two-sided limit is also 1. Notice that although the limit of our function as x approaches 2 from both sides is equal to 1, notice that, just a side note, f of 2 is actually equal to 2, right? F of 2 is actually equal to 2. Even though f of 2 is equal to 2, the limit of our function as x approaches 2 is equal to 1. Okay, let's go to a new interior point. Let's go to x equal to 3. All right, keep in mind that 3 is an interior point. It's not a boundary point or an endpoint, okay? So the limit of our function as x approaches 3 from the left. All right, so x values are approaching 3 from the left. Your function values are approaching 2. The limit of our function as x approaches 3 from the right. All right, so x values are approaching 3 from the right. Your function values are approaching 2. Now, I don't even need to look at the graph. I know this two-sided limit, the limit of our function as x approaches 3, from both sides of 3 must be equal to 2. I'm not even looking at my graph, right? So I know that it must be equal to 2 because these two one-sided limits are 2. Now, notice that all of these values are 2, and also notice that f of 3 is also 2, right? The function value at 3 is equal to the limit. Notice the equality of the limit and the function value. The equality of the limit and the function value. That has everything to do with something we're going to talk about called continuity. Continuity at that point 3, okay? All right, let's go to the boundary point 4. All right, here we go, folks. The limit of our function as x approaches 4 from the left. So here we go. X values are approaching 4 from the left. Your function values are approaching 1. Very good. The limit of our function as x values approach 4 from the right. Wait a minute. 4 from the right, the function is not even defined for x values to the right of 4. So we're going to say this one-sided limit does not exist. All right. Now, remember that this value 4 is a boundary point. 4 is a boundary point. So we can say that the limit of our function as x approaches 4, as x approaches that boundary point, we can say this limit exists as long as a one-sided limit exists at 4. And it does. This one-sided limit exists as x approaches 4 from the left. Therefore, the limit of our function as x approaches 4, that boundary point, that endpoint, is equal to 1. All right. Very good. All right, here's an important limit that we're going to use a lot, and it's the limit of sine of theta over theta as theta approaches 0 is equal to 1. And here theta is in radians. Let's see if we can prove this. And to make the proof a little more clear to see, I'm going to draw a geometric proof here, or use a geometric proof. And I'm going to take you to the unit circle. I'm going to take you to quadrant 1 of the unit circle. So consider the following. I've drawn two triangles here. We have triangle OBC and we have triangle OAD. Something else I would like you to see is the sector OAC, this sector here. So that's a sector of the circle. All right, cool. All right, so what I think you all will agree with is that the area of triangle OAD, this area here, this smaller triangle, is less than the area of the sector OAC, which in turn is less than the area of the larger triangle OBC. Now let's consider what these areas are, okay? But before we do that, please note that this is the unit circle. So OA, this line segment OA, is equal to OC, which is both equal to 1 because this is the unit circle. This is the circle that is centered at the origin whose radius is 1. So then this line segment OA is equal to OC, which is equal to 1. Let's add that. Furthermore, I would like us to consider, so here's theta here. I would like us to consider what sine of theta is, and what cosine of theta is, and what tangent of theta is. Now, sine of theta, remember sine is opposite over hypotenuse. So sine of theta is going to be AD over OA. AD over OA. But remember, we just said that OA is equal to 1, so then sine of theta is simply AD. Okay, cosine of theta, remember cosine is defined to be adjacent over hypotenuse. So cosine of theta will be OD over OA. Again, OA is equal to 1, so then cosine of theta is simply OD. Finally, tangent of theta. Tangent of theta, I guess I can make that theta nicer there. Tangent of theta, remember it's opposite over adjacent, and watch this. I'm going to say tangent of theta is equal to this opposite side of this larger triangle. So opposite over adjacent. So BC over OC. BC over OC. But again, OC is equal to 1, right? OC is equal to 1 because this is the unit circle. So then tangent of theta is simply BC. Okay, with all that being said, I would like us for now to consider what is the area of this triangle OAD. Now remember that the traditional formula for the area of a triangle is 1/2 times base times height. 1/2 base times height. So this triangle here, OAD, which is the smaller triangle, it has area 1/2 times the base, which is OD, times the height, AD. Okay, folks, and this is what we have. The area of the smaller triangle, OAD, is 1/2 times the base, OD, times the height, which is AD. So I have half OD, AD. The area of the sector, remember the formula for the area of a sector is 1/2 times the radius squared times the radian measure of your angle theta. So it's 1/2 times the radius squared. Remember, this is a unit circle, so the radius is 1, times the radian measure of theta. That's the area of this sector. Finally, the area of the larger triangle is 1/2 times the base, so it's OC, and the height, which is BC. Now, remember that, again, we have OD here. OD, we found, is equivalent to cosine theta, so I'll make that substitution for OD. And AD is, we found, is sine of theta. Okay, OD is cosine theta, AD is sine of theta. So we'll make that that substitution there. Similarly, while this is just theta over 2, I'll write it like that, theta over 2. And this here is 1/2 times. Now, OC is equal to 1, right? And BC is equal to tangent theta. So I'll make those substitutions now. So this is what we have. Half cosine theta times sine of theta is less than theta over 2, which is less than 1/2 tangent theta. What I'm going to do is I'm going to multiply everything by 2, and that will lead me to cosine theta. Sine theta is less than theta, which is less than tangent theta. I multiplied each expression of this inequality by 2. Now, what I would like us to consider is tangent of theta. See if I can write this. That is pretty sloppy. Let me see. I feel bad that how sloppy that is. Let me rewrite that. Cosine theta, that's a little better, times sine of theta is less than theta, which is less than. Now, by the quotient identity for tangent, tangent of theta is equivalent to sine of theta over cosine theta. Now, at this point, you may want to remember what it is we're trying to do. We're trying to show that the limit, you can go back in your notes, but it says the limit as theta approaches 0 of sine of theta over theta. Sine of theta over theta. All I have right now is theta. I need sine of theta over theta. All right, so what I would invite you to do is to divide each of these expressions by sine of theta. Like that. What that would lead you to is simply cosine theta over here is less than theta over sine theta, which is less than 1 over cosine theta. All right. Now let me see if I can move. Well, yeah, I can move this. I don't have to erase. I can just move this up. Okay, like that. I think that's good. Okay, and what I would like to do now is I would like to reciprocate this inequality. So I would like to, take reciprocals of each one of these expressions. But what that does is it reverses the inequality. So in other words, we would have 1 over cosine theta. That's the reciprocal of cosine theta. And then the reciprocal of theta over sine theta is exactly the expression we're talking about, sine theta over theta. There it is. I'm sorry, it reverses the inequality. So this inequality should have been reversed. So let's change that. That's a mistake. Let me see if I can just erase that. There we go. Anyway, so because we're reciprocating, these inequalities are now reversed. There, that looks a little better. And which is greater than, now this is cosine theta. Okay, what I would like us to do is rewrite this inequality from right to left. So from right to left, it is cosine theta, I'm reading now from right to left, is less than sine of theta over theta, which is less than 1 over cosine theta. All right, very good. Let me move this up again. Now, you remember the sandwich or squeeze theorem? I want you to consider this. Now consider the limit of cosine of theta as theta approaches 0. That's equal to, do you remember? It's equal to 1, which is equal to the limit of 1 over cosine theta as theta approaches 0, right? Because the limit of cosine of theta as theta approaches 0 is 1, so then this is 1 over 1, which is 1. So notice how this expression, this function, sine of theta over theta, is sandwiched between this expression and this one. And the limit of this expression as theta goes to 0 is equal to 1. The limit of this expression as theta goes to 0 is also equal to 1. Therefore, by the sandwich theorem, the limit of sine of theta over theta as theta approaches 0 must also be 1. So we have the limit of sine of theta over theta as theta approaches 0 is equal to 1. All right, we did it. All right, let's find, not fine, sorry about that, find each limit. All right, so this is the first limit I have us considering, the limit of cosine of y minus 1 all over y as y approaches 0. All right, we're going to have to be really clever here. So the first thing I would like us to do is to remember the half angle identity for cosine, because I'm going to use that to rewrite the numerator in terms of sine. Why would I want to rewrite the numerator in terms of sine? So that I can use what we just showed, right? Sine of theta over theta is equal to 1, right? I should say the limit of this expression as theta goes to 0. Oops, I'm sorry. It's a 0. Is equal to 1. So I would like to use this, but the only problem is, well, I don't have sine of theta over theta. So I want to be clever and use some identities so that I can rewrite this expression so that it's of the form sine of theta over theta. Okay, so come with me really quickly. I want to remind you that cosine of y over 2, that's a half angle, right, is equal to plus or minus the square root of 1 plus cosine of y over 2. Okay, that 2 right here is underneath the square root. I can square both sides, so stay with me. So if I square both sides, then cosine squared of y over 2 is equal to 1 plus cosine y, all of that over 2. Now, remember the Pythagorean identity? The Pythagorean identity says sine squared of theta plus cosine squared of theta is equal to 1, right? That means that cosine squared of theta is equal to 1 minus sine squared of theta. So I can use this here, this identity, to say that cosine squared of this angle, y over 2, is equivalent to 1 minus sine squared of that angle. Let's put that in parentheses. I should have had this in parentheses the entire time. There. So we have 1 minus sine squared of y over 2 is equal to 1 plus cosine of y over 2. All right, let's move this screen up a little bit. Let's multiply both sides by 2. And I get 2 minus 2 times sine squared of y over 2 is equal to 1 plus cosine of y. If I isolate this sine squared expression, or at least just subtract 2 from both sides, I get negative 2 sine squared of y over 2. I'm subtracting 2 from both sides. So subtract 2, you get negative 1 plus cosine of y. That is to say, negative 2 sine squared of y over 2 is equal to, watch this, cosine of y minus 1. This here is what our numerator is. That's what our numerator is, cosine of y minus 1. We can replace this with negative 2 sine squared of y over 2. All right, so I'm going all the way back. Oops, there we go. Let's go all the way back. Keep coming, keep coming. I'm going to replace this here, this expression, cosine of y minus 1, with negative 2 sine squared of y over 2. All right, so let's do that now. All right, so this is what we have. What we can do is we can pull out that negative really quickly. So the negative is here. So the numerator is 2 times sine squared of y over 2. Now, all of this over y. What I would like to do is make a substitution. I would like to say, let me see if I can write this out for you. Okay, so let theta equal y over 2. All right, if theta is equal to y over 2, that's equivalent to saying that y is equal to 2 theta. All right, so let's make that substitution. All right, let me move this up just a little bit here. There, that's good enough. All right, so what we have is the limit. Let's see. So we have a negative right here, and we have 2 times sine squared of theta over 2 theta. All right. There should be parentheses, I guess, around all of this. And now this is no longer y is going to 0. Now we have theta is going to 0, right? Because this expression is now written in terms of theta. You can see that we're getting really close, right? So this, I can pull out this negative in front of the limit, and I have negative the limit of, as theta goes to 0. You see these 2's They cancel out. All right, great. And I'm going to rewrite this as sine of theta, watch this, over theta times sine of theta, right? Because this is sine squared of theta, which means sine of theta times sine of theta, right? That's what this means. So here's sine of theta times sine of theta. That's sine squared of theta, okay? So now we can actually plug this in. We can plug theta equal to 0 in. We have negative, and we know that sine of theta over theta as theta goes to 0 is 1. And sine of theta as theta goes to 0 is 0. So then this entire limit is equal to 0. This is our final answer. This is the limit. All right, next one. The limit of this expression as x goes to 0. Now, unfortunately, what we have is sine of theta over theta, the limit as theta goes to 0, right? This is equal to 1. This expression, it's close. I mean, what you would really want, right, is if I can make a wish, it would be the limit of sine of 2x, that's what we have in the numerator, over 2x as x goes to 0. This would be great because then we can say the limit is equal to 1. You know what I mean? It's sine of this argument over that same argument, right? Sine of that angle over that angle. That's sine of this angle over that same angle. Anyway, it would apply, right? But that's not what we have. We have a 5x down here. We need this to be a 2x. If this were a 2x, then it would be great. So we need a 2x in the denominator. So what we're going to do is we need a 2 down here, so we're actually going to multiply by exactly what we need. I need this 5 to go away, and I need it to be replaced with a 2. All right? So let me get rid of this here. So this is what I'm going to do. The limit as x goes to 0. Again, I need this 5 to go away. If I divide 5 by itself, if I divide 5 by 5, then it goes away. But I also need it to be replaced with a 2. So in other words, let's do the following. What if I multiply this by 2/5? What that would do is that would allow me to divide out the 5, and I'll be left with 2x down here, which is exactly what we need. But you and I know that if you multiply the denominator by 2/5, you should multiply the numerator by 2/5 as well. Correct, everybody? Let me rewrite this so that it's a proper notation. So then this would be the limit as x approaches 0 of the numerator would be 2/5 times sine of 2x and then over 2x. Right, everybody? Now this 2/5 here can be pulled out in front of the limit. So then this is now 2/5 times the limit as x approaches 0 of, watch this, sine of 2x over 2x. So this is exactly what we needed. Now we can use our findings, right? This is 2/5 times 1. So then the limit is 2/5. Wasn't that clever? Good job. All right. Let's make this example the last one. All right. So we want to find this limit. All right, folks. The limit of tan t secant 2t all over 3t as t goes to 0. All right. So what I would like to do is I would like to rewrite this expression. So let's consider this. The limit as t goes to 0. I would like to write this as 1/3. Instead of dividing by 3, I want to write it as multiplying by 1/3. Also, instead of dividing by t, I want to write that as multiplying by 1 over t, right? And then you have tan t times secant of 2t. All right, very good. I want to continue rewriting this. So this is, first of all, we can go, let me go back just for a second there. All right, so we can pull out the 1/3, right, as a constant. So 1/3 times the limit as t goes to 0. Now I have 1 over t times tangent of t by the quotient identity is sine of t over cosine of t, and secant of 2t by the reciprocal identity, its reciprocal identity is equal to 1 over cosine of 2t. All right, very good. So let me move this. I would like to rearrange these terms to be 1/3 times the limit as t goes to 0. I'm going to rewrite this here, sine of t over t. Do you see that? So sine of t over t, you know that's convenient, right? That looks like our sine of theta over theta, right? So that takes care of this factor and this one. And then what I have left is 1 over cosine of t times 1 over cosine of 2t. Now, we can actually evaluate this. This is 1/3 times. Now, this expression, sine of t over t as t goes to 0, we already proved that that's equal to 1. And the limit of cosine of t as t goes to 0 is 1. So this is 1 over 1, which is equal to 1. Likewise, as t goes to 0, cosine of 2t is approaching cosine of 0, which is 1. So this is 1 over 1 as well. So then our final answer is 1/3. 1/3. This is the limit. Very good, folks.